Hello, good afternoon, everyone. Welcome to the week 6. Good afternoon, everyone. Welcome to the week 6 of this tutorial session of this course Principles of Modern CDMA, MIMO, OFDM Wireless Communication. So, today we are going to solve some of the questions which is taught in the week 6. So, concepts will be related to the week 6 lectures. So basically, first we will see the multi-user CDMA system. Then we will study about the MIMO system and the rake receiver, and we will solve a question related to that. So first we will see SINR, signal is to interference and noise ratio in multi-user CDMA system. So in multi-user CDMA, what we have studied in the last lecture, like let's suppose there is a two user 0 and user 1. And the symbol transmitted to the user 0 is A0 and for user 1 is A1, and let's suppose the power is given as P1 and P0. So power is given as P0 and power for the user 1 is given as P1. And in CDMA system we have seen that orthogonal code is assigned to each user so that at the receiver end the code can be recovered correctly. So the X0 N, the transmitted symbol X0 N will be A0 C0 N, and for X1 N it will be A1 C1 N. So this C0 N and C1 N is the code. This is orthogonal to each other. And the complete transmitted symbol is Xn, that is X0 N plus X1 N. So like there are two users, so transmitter at the base station is transmitting Xn, and that is for the user 0 and user 1. So received symbol Yn at the user will be Xn plus Wn. Wn is the noise. So what will be here Xn? Xn will become X0 N plus X1 N. So X0 N is A0 C0 N plus A1 C1 N plus Wn. Okay, let's take this equation 1, and this is our additive white Gaussian noise. And we know that the mean of this noise symbol will be 0 and variance will be sigma n squared. And also expectation of this noise are independent to each other. So two noise symbol will be 0 if n1 is not equal to n2, and this will become sigma squared if n1 is equal to n2. Okay, so from here only we can find this noise power. So now for user 0, we will use code C naught to recover the signal. Like this complete yn will be received at the user 0, but we will use for user 0 what we will use code C naught to recover the signal. So here in this case, so we'll multiply like yn with C naught n. And where we will like correlate with the code C naught n for the user 0, and we'll normalize it with n. So now this we can write it as so this is correlation with code 0, so we can write correlation symbol r naught. So here we can write this as 1 by n. Yn is this, so we can take a naught C naught n plus a1 C1 n plus wn multiplied with C naught n. So from here we will get two terms. One the C naught squared n term, and another we will get C1 n and C naught n term. So the first term will be and one more thing I forgot here, it will be HXN because the channel response also will be there. So here we can write this H also. So now we know that this signal 1 by n summation h a naught C naught squared n. So this is for desired for user 0, and the another one is the interference signal a1 C1 n C naught n. So this is the interference. So now, and there will be additional term, that is the noise term. So noise will be 1 by n summation of wn C naught n. So now let's take the desired component. The desired is 1 by n a naught, c naught, and c naught n. So this we can write as a naught 1 by n summation of c naught square n. So in last lecture we have seen the properties of this code. So this if like this summation will become summation of 1, and if like n minus I, so this will become 1 if I is equal to 0, and this will become 0 if uh, I is not equal to 0. So we will use that concept. So this part will be a naught 1 by n summation of 1. So this summation will become n. So a naught by n into n. So it will become a naught. Okay. An interference signal will become 1 by n.
So this H will also come, no?
Yes, h will also come. So we can take this as a h a naught. So this is our desired signal. And if we take the unity channel gain, then we can reduce this h also. So we can directly write a naught. And for the interference signal, this will sum out to be 1 by n. There is the code C1n and C0n. So this C1n and C0n, we can write the correlation R01 A1 into R01 multiplied with 0. And this n will also go, because yesterday what we have studied, R01 is 1 by n summation of C0n and C1n. So in this case, this is the interference signal now. So that is the correlation one. So in the last lecture, uh, let's go through that once. So here what we have seen, this correlation is equal to 1 if n naught is equal to 0, and it will be minus 1 by n when n naught is not equal to 0. But in our case, there is a correlation between two symbols, R0, 1. So that will be 1 by n here. So this term we will write 1 by n, R0 1 by n. So it will become this is our interference signal. So when we write the power, interference power, it will become expectation of this signal. So that is A1 R01 mod square So this will become expectation of this A1 and R01 are independent. So we can take like this. So this A1, the power of P1 into 1 by n. So this is P1 by n. And for this, the expectation of A naught square, this will be P naught. So now this we can add as P naught. And the noise power, it will be sigma n squared by n. So this part is our noise. So this will be sigma n squared by n. So now the signal is to interference and noise, interference plus noise ratio will be P naught divided by sigma n squared by n. This is the noise, and interference is P1 by n. So here we can write P naught into n divided by P1 plus sigma n squared. So similarly, if like there are k plus 1 user, so the same formula can be derived. So SINR will be P naught n, and there will be how many interference? In this case, there will be k interference. So here there is only one interference because there is two users. So one is the desired signal, one is the interference signal from the second user. If k plus 1 user is there, then there will be k interference signal. So it will be pk, k is equal to 1 to k, and noise will be sigma n squared. So this was about the multi-user CDMA system, signal is to noise ratio. So there are some questions based on this formula. So we will remember this. This is the main, and then again we will solve the question. Now coming, and most of the questions are based on the MIMO system in today's lecture. So basically MIMO system stands for multiple input and multiple output system. So first we'll see little basics of MIMO system. Like in MIMO system, at the transmitter end there will be M output antenna, and at the receiver end there will be, let's suppose, N input antenna. So now this antenna can transmit to the all the users or some of the users based on if the user lies within the cell of that transmitter antenna. So it is having T transmit antenna, let's suppose, and R receive antenna. The first question is very easy. The special case of MIMO system with a single receive antenna and multiple transmit antenna. So like here in this question there will be only one receive antenna, like single receive antenna. So at the user terminal there will be only single receive antenna, and at the base station there will be multiple transmit antenna. So as you can see, T1, T2, Tn, and here it is user only one. So this is multiple transmit antenna. We'll come into the MIMO system, but the first question is very easy, so we'll solve. So this means multiple input and here there is single receive antenna. So the output is only one. As you can see, y is equal to h x plus n. So here x is x naught, x1, xn. Okay. So there is this is the input and this is the output. Okay. So there is multiple receive, multiple transmit antenna. So multiple input, and here it is a single output. So what we can say this, which kind of system it is? It is a multiple input and single output system. So this is a MISO system. So apart from this, now come to the MIMO system. So this is our MISO system. Multiple inputs, single output. And this is our MIMO system.
So, sir, can we say any mobile in our hand is a MISO because it has only one
No, no, no.
receiver?
In mobile also nowadays there are multiple receive antennas.
But if in mobile it is one antenna, then
Then we can say MISO. Nowadays in our like in a single mobile device, there can be a multiple receive antenna as well and multiple transmit antenna. But if it is having a single receive antenna, then we can say as a MISO. So now this is the R cross T MIMO system because there is R receive antenna and T transmit antenna. So now we will see how to represent this graphically. Sorry, in a matrix form. So X denotes the, like as we have seen, Y is equal to Hx plus N. So in this, X denotes the, like for the formula, Y is equal to Hx plus N. So here what is our X? X denotes the symbol transmitted. So let's come to the next page. So X denotes. So how many symbol will be transmitted here? Because there is T transmit antenna. So X denotes the T symbol transmitted from the T transmit antennas. Okay, so we can write X as X1, X2, dot 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 dot, XT. Okay, and here what is XI? XI denotes the symbol transmitted from the ith transmitter antenna. Now coming to the receiver end, so there are R receiver. So Y we can denote as Y1 to Y2 to YR, and here is the R received symbol, and YI denotes the symbol received by the ith received antenna. Okay, so basically in MIMO system, what happened? The transmit symbol is Xi and the received is Yi. And this is our MIMO channel. So the channel H can be denoted as HR cross T matrix. So this can be written as H11, H12, H1T, H21, H22, H2T, there will be HR2, and finally it will be HRT. So this is our R cross T matrix. So the complete MIMO system we can represent as Y1, Y2, So this is the received symbol. The dimension is r cross 1. There are lots of questions based on dimension also. So we will figure it out the dimension as well. And the channel matrix is H11, H12, H1T. This channel is R cross T, and this is uh, multiplied with our transmit symbol X, that is X1 to XT, and also we can see like this T and T should be equal. Then only this matrix multiplication can happen. And plus the noise vector. So noise is with R receiver. So it will be added at all the receiver N1 to NR. So again this will be R cross 1. So this is important. The received symbol is R cross 1. Transmit symbol is T cross 1. Channel vector is R cross T, and the noise vector is R cross 1. Okay. And also the received signal at uh, y1. Y1 means like the first receive antenna. So this we can write. This is the multiplication of first row in the channel vector with the column of mm, like h11 x1 plus h12 x2 dot 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 h1t xt plus n1. So this is our desired component, and these are interference, and this is noise. Okay, so now let's solve some questions. So in order to overcome the near far problem in CD, it's based on the near far problem. So basically, so let's study about the near far. So we'll see near far after a few minutes, but let's solve some of the questions based on this, uh, the dimensions of the MIMO system. So the question number 3 is the size of the noise vector at 5 cross 3 MIMO system. So 5 cross 3 MIMO system means H, the channel vector is 5 cross 3. So here, this is the uh, like number of receive antenna. And what is 3 here? 3 is number of transmit antenna. So where all noise will be added at all the receiver end. So number of receive antenna is 5. So the noise vector will be 5 cross 1. So the correct answer will be option number B. So a spatial multiplexing is possible in, so it is possible in MIMO system. So what is a spatial multiplexing? Like there are different data pipes between the user and the transmitter and the receiver end. So here you can see this is our transmitter and this is our receiver. So the symbol is transmitted through different data pipes. So transmit multiple information streams in parallel. So basically, spatial multiplexing is transmit multiple information streams in parallel. So for this, the correct answer is for question number 4 is MIMO system. So which receiver is employed in CDMA system to exploit multipath diversity? It's a rake receiver. We will see this concept also. So better first look at those concepts and solve the question number 2 and question number 5. So question number 2 is based on near far problem. So we'll see what is near far problem. So let's suppose like this is our transmitter, like this is our base station, and a user is situated very near to it, and the power transmitted is P1, and one user is situated very far to it, P0. Okay. So for transmitting symbol, like in this like near far problem, what we have to do, like to avoid this, we have to transmit lower power to user which is nearby, because it is nearby. So P1 should be less than P0, and higher power transmission to the user which is far. Why so? Let's see first. So P1 should be less than P0. So this mechanism is the power control. So the correct answer is power control. But let's see why we have to think like that. So SINR at the user 0 of two user CDMA system as derived earlier can be given as SINR is equal to P0 divided by P1 and plus noise. Let me check once this video is getting recorded or not. So okay, so this is SINR. Now let's suppose like the equation this user is situated at d1 distance, and this user is situated at d0 distance, and let's suppose d0 is equal to square root of n d1, and then power is inversely proportional, power transmitted is inversely proportional to the distance of a square. So P1 is equal to PT by D0 square, because and PT is the transmitted power. So here we can write D0 as square root of n d1, so it will become n d1 square. Okay. Similarly, P0 is equal to PT by So SINR at the user 0 is here. So let D naught is equal to the square root of n d1, and power is inversely proportional to d square. So we can write P naught is Pt by T is inversely proportional to d square. So P1 we can write transmitted power by d naught square. So again here we can write Pt by d naught square. So it will become n d1 square. So now SINR will be, and let's suppose like so Pt by n d1 square divided by Pt by n d1 square plus this noise is sigma n square divided by n. So this we can write it as Pt by Pt plus sigma n square d1 square into this n and n will get cancelled. So here we can see, so this both symbol have the same transmitted power, like the interference signal is equal to the interference is very strong interference here. So to avoid this near far problem, what we have to do, what is the like the same thing what we have discussed here. So this is a near far problem. Like if we allocate the same power like PT in that case what we have studied, then like uh, there will be a strong interference to the signal which is nearby. So we have to like to avoid near far problem in CDMA system, we have to transmit lower power to user which is near by to the base station, and higher power to user which is far from base station. The same question is there. So it should be P1 should be less than P0 because this is user nearby. So P1 should be less. So this mechanism also known as power control strategies. So this is used to overcome the near far problem in CDMA system. Now coming to the question number 6, that is based on the properties of PN sequence, what we have studied yesterday. So if the total number of runs in PN sequence is 128, then the number of runs of length 3 is. So number of runs of length 3 is equal to 1 by 2 to the power of 3 into total number of runs, that is 128. What is the formula? Formula is number of runs of length n is equal to 1 by 2 to the power of n into total number of runs. The same formula we will apply. So 1 by 8 into 128. So this will become 116. So option C is the correct answer. So number of runs of length 3 is 16. Coming to question number 7. The size of the transmit vector is 5 cross 3 MIMO system. So again, the channel matrix is 5 cross 3. because it is given 5 cross 3 MIMO system. So uh, it is 5 cross 3, so there is 5 receive antenna. So because H R cross T. So the first term is like the number of rows is the number of receive antennas, and this is transmit antenna. And this is HX, so X will be what? 3 cross 1. So simple. So here our X is 3 cross 1. So the size of the transmit vector. So this is transmit vector. So it is 3. So vector of size 3. Option A is the correct answer for this question. Now coming to the question number 8. Consider a MIMO channel matrix below. H is equal to 2 minus 1 minus 1 2 2 2. Maybe in this class, like in this week, zero forcing matrices might not be taught. So ZF receiver, I think it is taught in the previous week. So is H transmission H inverse into H of transport. Sorry, H transport. So here, if it is complex, then we can take Hermitian, H Hermitian. So also, or H Hermitian H inverse into H Hermitian. But it is a real values like for this channel matrix. So this is H is given. So first we will find H transpose H. So this will become transpose of this will become 2 minus 1 2 minus 1 2 2, and H is 2 minus 1 minus 1 2 2 2. So this is our 2 cross 3, and this is 3 cross 2. So the final matrix will be 2 cross 2. So when you multiply 4 plus 1 5 plus 4 9 minus 2 minus 2 minus 4 plus 0. This will become 0 minus 2 minus 2 minus 4 plus 4 0, and this will become 1 plus 4 plus 4. So this is H transpose H. Now the inverse of this H transpose H inverse. This is simply do the determinant of that 1 by 81 and just exchange these two and take the conjugate of this element. So this will become 0 9. So this is the H transpose H inverse. So now we have to just multiply. So ZF receiver is H transpose H inverse into H transpose. 2 minus 1 2 minus 1 2. So this is our final value, and here we can divide it by 9 also. So we'll get 1 by 9. And when you take 9 common, it will become 2 minus 1 2 minus 1 2. So the correct option is 1 by 9 2 minus 1 2 minus 1 2 2. So option D is the correct answer for this question. Now coming to the question number 9. The transmission of multiple information streams in parallel in a MIMO system with multiple transmit antennas and multiple receive antennas is termed as spatial multiplexing, what we have studied in the beginning. Now come to the question number 10. So in a 3 cross 2 MIMO system with the noise element variance is given as minus 6 dB. So sigma square is equal to minus 6 dB. So let's calculate the value of sigma squared. So it will be equal to 10 to the power of minus 0.6. Okay. So this value will be around 0.25. So the noise covariance matrix is given as sigma square I r cross r. And this is a 3 cross 2 MIMO system. So R is equal to 3 here. So the noise covariance matrix will be sigma squared I 3 cross 3. I is the identity matrix. So we can write here 0 0.25, 1, 0, 0, 0, 1, 0, 0, 0, 1. So, or also we can write 1 by 4 I 3 cross 3. So the correct answer is option number C. So we can see this, there was a question on rake receiver. Question number 5. So we'll see what is rake receiver. Let's suppose like yn is a received symbol that is given as h0 xn. So h and x is the convolution matrix. So we can write h1 x n minus 1 plus h of l minus 1 x of n minus l plus 1 plus wn. So we can simply write hl x of n minus l plus w, and here xn is equal to in CDMA a naught c naught n. So yn is equal to summation of hl a naught c naught n minus l plus wn. Okay. So in rake receiver we are taking maximal ratio combiner. So SNR with MRC in this case I will directly write this will be first the h squared into power divided by the noise power. So this we can write like this. So so in rake receiver basically the SINR is maximized using the maximal ratio combiner. So today we have this much only. And what is MRC? So MRC is the like so here optimal processing is done using maximal ratio combiner. This is given as let's suppose if it is on vector r, then this can be written as h bar Hermitian divided by mod of h bar in the direction of r bar. This means this is a unit vector. So this is the rake receiver in the, like, applying the maximal ratio combiner on the vector is the rake receiver in CDMA. And this is the SNR with the MRs. So one last question we'll solve and then we'll end the lecture here. So consider a MIMO system with R is equal to 3 receive antenna and the noise variance is given minus 3 dB. So find the noise covariance matrix. So for solving this question, so the noise covariance matrix is, as we have studied here, it is the variance square into the identity matrix. So this can be given as R is equal to sigma square I 3 cross 3, because here R is equal to 3 receive antenna and sigma square in dB is given as minus 3 dB. So 10 log 10 sigma square is equal to minus 3. So what is the value of sigma square? That is 10 to the power of minus 0.3. This is 1 by 2. So here R will be 1 by 2 identity matrix 3 cross 3. So the noise covariance matrix is half 1 0 0 0 1 0 0 0 1. So today we'll end up the lecture here only. So we'll meet next again on the Saturday 3 to 5 p.m. So thank you everyone for attending today's lecture. You can ask if you want to ask anything, else we can cut the call. So thank you. We'll meet again in the next week at the same time.